So, hello everyone. This side Mayank Jhunjhunwala from IIT Kanpur. So, we were doing questions on electromagnetic induction in our last session. So, let's continue with that. We had completed till question number 18, and today we will start with question number 19. So, let's start. So, it is saying a conductor of length 0.4 meter is moving with a speed of 7 meter per second perpendicular to magnetic field of intensity this much. So, B vector magnitude is given to us as zero point 0.9 Weber per meter square. It is zero point 0.9 Tesla. Okay. And EMF induced is being asked to us. Okay, it is again same question. So let's see. So we know that EMF is given by d phi by dt. And in case of a conductor which is a straight wire, it is B. Actually, it would be BLV sine theta. The sign is basically to get the perpendicular component. So everything is given to us. B is given to us zero point 0.9. L is also given as 0.4. V is 7. And they are saying that it is perpendicular to magnetic field. So theta would be 90 degrees. Just put on the values. E equals BLV sine theta. Put each value. B is zero point 0.9. L is 0.4. V is 7 into sine 90. Okay. So solving this, you will get your final answer, which is 2.52 volts. Option number B. Pretty simple question. Just use this formula and you will get your answer. So moving on to next one. Number 20. Varying current in a coil changes from 10 ampere to 0 in zero point 0.5 seconds. So they are basically saying that current changes from 10 to 0 in zero point 0.5 seconds. So from here I can calculate delta I by delta t, which is 10 minus 0 by zero point 0.5. That is 20 amperes per second. Cool. If the average EMF induced in the coil is 220 volts, so average EMF induced is given to us 220 volts. Then what will be the self-inductance of the coil? Okay, so again a simple one. You know that self-inductance for flux in terms of self-inductance is given by Li. So EMF induced equals minus d phi by dt. That is minus d by dt of Li. That is minus L di by dt. Okay. For average, this would be equal to minus L delta I by delta t. Cool. So just put on the values and we will get the self-inductance value. So L would be equal to EMF induced upon delta I by delta t. So it is 220 volts divided by 20 ampere per second. This will give us 11 henries as our final answer, which is option number C. Cool. So just use this formula. EMF induced is equals minus L di by dt. Di by dt is given to us in average form. So EMF induced is also average. We use both of these values and we get to our final answer, which is value for inductance is given by 11 henries. Okay. So again a simple one. Moving on to next one. Question number 21. An electron moves on a straight line path x, y as shown. So an electron is moving like this. This is x. And ABCD is a coil adjacent to the path of electron. This is coil which is adjacent to the path of electron, means in the same plane. What will the direction of current, if any, induced? Basically, they are asking that an electron is moving like this in xy path, and due to this movement of electron, will there be any current induced in this ABCD coil? And if it will be induced, then tell me the direction also. Okay, so it would be ADCB, current will induce in reverse direction, no current induced, or ABCD or ADCB. So basically like this or this. due to this movement of electron. How will the current be induced in this coil? We have to answer that thing. So let's see. So current will be induced when electron comes closer. The induced current will be anticlockwise. When electron comes farther, it will be clockwise. So basically, what is happening here is when electron is coming closer to us, then flux is increasing. So when it is coming closer, the current will flow in this in anticlockwise direction. Why so? Because flux is increasing in inward direction. When this electron is coming closer to the loop, then when you will use your right hand thumb rule, then flux will increase in inward direction. So to counter that, using Lenz's law, there should be a current in the coil which should flow in the opposite direction to induce to oppose this induced EMF. That's why the current will flow in anticlockwise direction. Similarly, when electron will go away, then flux will start reducing in inside direction. So again, according to Lenz's law, the induced current will try to oppose the change in magnetic field. So this time the current will be induced clockwise to increase the inward flux. So initially, when electron is approaching, flux increases in inward direction. So anticlockwise current will be established. Anticlock current will come to oppose it. Similarly, when electron is going back, flux will decrease. So to increase it, we will have current in clockwise direction. Cool. So this is nothing but only application of Lenz's law to oppose the change in magnetic flux. Cool. So initially it would be anti-clockwise, and then when it recedes back, it would be clockwise. So this is my option number B. The current will reverse its direction as electron goes past the coil. Initially it is anti-clockwise like this, and then it will become clockwise like this. It's just based on Lenz's law. Cool. So let's move on to question number 22. What is the self-inductance of a coil which produces 5 volts? The current changes from 3 ampere to 2 ampere in 1 millisecond. Again, the same question, similar question we did question number 28, I guess. So EMF induced is given to us as 5 volts. We can calculate delta I by delta t. Since it is millisecond, so I think I should take di by dt. That would be 3 minus 2 upon 1 millisecond. Millisecond is 10 power minus 3. So it would be 10 power 3 amperes per second. So EMF induced would be given by L times delta I by delta t. So again, L would be EMF induced upon delta I by delta t. Cool. So it would be 5 upon 10 power 3. That is 5 into 10 power minus 3 Henry. Or we can write it as 5 millihenry, which is option number B. So option number B is our right answer. Again, a simple question. We know EMF induced is given by d phi by dt. And in case of self-inductance, phi is Li. So just use this thing, you will get L di by dt. Of course, I'm talking about magnitude. Cool. So just put on the values and you will get your final answer as option number B. Okay, so let's move on to question number 23. If n is the number of turns in a coil, the value of self-inductance varies as okay. So basically it is asking how L is depending, how L depends upon number of turns. So it is again a very standard question. Uh, Basically, for different geometries, how is L dependent on number of turns in? Okay, so basically from here I can see phi is given by Li. For total flux, I need to multiply by number of turns. So from here, L is given by N phi by I. This is N phi by I. Okay. So phi is given by B into A into cos theta. So put the value of phi N B A by I. For now, they are asking for a coil. So let's take a circle. We can take any geometry. So they are taking circle here. So let's take a circle. And B would be given by mu naught N I A upon 2R into I. So I and I will get cancelled, and you would be left with n square, basically directly proportional. The rest all terms I would take into proportionality constant. So I would be left with two n's, basically these two. One is this and one is this one. So it would be proportional to n square. This is for circle or straight wire. You can take any geometry, you will get n square only because it doesn't depend upon geometry. It is independent of geometry. It is common for all that L is dependent upon n square, where n is number of turns. Okay, so please remember this thing. This derivation is okay, but for exam point of view, if you are having a hold of this, and so you can directly mark it and move ahead, it will save your time only. So please remember that self-inductance is directly proportional to the square of number of turns. So it would be option number C. Pretty simple question again. So let's move ahead now. Question number 24. A rectangular coil of 20 turns and area of cross section this much. N is 20. Area of cross section is 25 centimeter square. Has a resistance of 100 ohms. If a magnetic field which is perpendicular to the plane of coil, the changes at the rate of this thing. So basically, dB by dt is given to me 1000 Tesla per second. The current in the coil is how much? Okay, so basically, how much is the current? They are asking me this thing. So everything is given to me. R is I know that I is given by V by R. So I need to calculate V. And V is nothing but the induced EMF, which would be given by d phi by dt. Okay, so let's see. So I is given by E by R, E is given by d phi by dt, where phi is nothing but N B A cos theta. So since it is perpendicular, so area vector and B would be parallel to each other because area vector is perpendicular to the geometry. So since both are parallel, theta would be 0 degrees, cos theta cos 0 would be 1. So it would be, so to calculate d phi by dt, n is a constant, area is a constant, it would be dB by dt. And cos theta would be 1. So that's what I have written here, NA dB by dt. So I would be E by R, which would be NB, sorry, it would be NA dB by dt upon R. N is given to us as NA dB, N is how much? N is 20, A is 25 centimeter square. So 20, 25 centimeter square, we need to convert it into meter. So multiply by 10 power minus 4. dB by dt is 1000. Divide by resistance. Resistance is how much? 1000, 100 ohms. So divide by 100 ohms. Just solve this. You will get 5 here and 5 here. So it would be 5 into 10 power minus 1. That is 0.5. So 0.5 ampere would be your final answer, which is your option number C. Okay. So again, simple question. You have to just use this formula that phi is given by BA cos theta, and cos phi is B dot A, and using these two formulas only will give you your final answer. Okay. And theta is 0 degree. I explained you why, because they are saying that magnetic field is perpendicular to the plane of coil. So if magnetic field is like this, then plane of coil would be something like this. So area vector would be like this or this only, which is parallel or anti-parallel to this thing. For both of the cases, cos theta would be 1. And since I'm talking only about magnitude, so I would neglect the minus sign. Cool. So this was my question number 24. Basic mathematics, and we will get our final answer. So moving on, question number 25. The total charge induced in the conducting loop when it is moved in a magnetic field depends on the rate of change of magnetic flux, initial magnetic flux only, total change in magnetic flux, final magnetic flux only. So it would depend upon rate of change of magnetic flux, which we are doing from a very long time. So this is the case. Total change. Okay, sorry. It's not about magnetic flux. It's not. It's only about the charge. Sorry for the confusion. It's for the charge. It's not about magnetic flux. So total charge induced in the conducting loop. So Q, we need to tell about Q, and Q is given by I into T, which is V by R into T. Okay. So let's see here. I dt V by R into T, because V is given by E induced. So it would be integration of E dt by R as shown here. E is again d phi by dt. So it would be 1 by R integration d phi by dt into dt. So this and this will cancel, it will become integration d phi by R. So this d phi, charge q is dependent upon this thing, integration of d phi, which is total charge induced, is depends upon the total change in magnetic flux, because integration d phi is nothing but total change in magnetic flux. If it would ask us about the why I initially took A, because EMF induced is dependent upon rate of change of magnetic flux, but they are not asking about EMF, they are asking about total charge. And total charge is nothing but integration of d phi by R. So it only depends upon total change in magnetic flux, not upon the rate. This integration d phi is total change in magnetic flux. And d phi by dt is called rate of change of magnetic flux. Okay. So EMF is depending upon this, and total charge Q is dependent upon this. Since they're asking about total charge, so C is the right answer. Cool. So this derivation is also very easy, and you should remember this thing also, that Q is integration d phi by R. These are basic things. If you will remember these things, it will save you a lot of time in JEE Mains exam. So please remember these things. So moving ahead with question number 26. A 100 millihenry coil. So inductance is given to us as 100 millihenry, which is 100 into 10 power minus 3 henries. I hope you know that milli is 10 power minus 3, micro is 10 power minus 6, and nano is 10 power minus 9. These are basic convention, and you should remember these three at least. Okay. There is a current of 1 ampere, so I is given to us as 1 ampere. Energy stored in the magnetic field. It was asked in 1991. So again, this is a simple direct question. If you know the formula for energy, is given by half into inductance into current induced square. Current induced squared. Okay. So half Li square which is half, into inductance is 100 millihenries. It would be 100 into 10 power minus 3 into current squared. Current is 1 ampere. So it would be 1 into 1 only. So it will cancel, and we would be left with 50 into 10 power minus 3. That is 50. Sorry. That would be 50 millijoules. Or you can write it as 0.05, which is option number C. Okay? Because 50 into 10 power minus 3 can be written as 0.005. So either write it like this or you can say it 50 millijoules. Both are correct. So it is a simple question. Just you have to know this formula. E is given by half Li square. Knowing this formula will only work. So option number C, again a very simple one. Just use this formula. And what this formula basically tells us, this formula tells us, let me clear the space. So this formula tells us amount of energy stored in an inductor when current flows through it. And this is the same energy which is released when in case of discharging. Okay. So this was about this question. Again, a simple one only. So now moving ahead to question number 27. So it is written here also. In building a steady current in the circuit, the source EMF has to do work against self-inductance of the coil, and whatever energy consumed for this work is stored in the magnetic field in form of magnetic potential energy of coil given by half Li square. Okay, so this is it. This shown here, and how this comes. If you write L, we know that phi is nothing but Li. So replace L with phi by I. So you will get half pi upon I into I square. This I and I will get cancelled. So you will get pi I by 2, and for number of turns n, this is for one turn, for total number of turns multiplied by n. So it would be equal to n phi I by 2, which is nothing but half n Li squared. Okay, so let's move ahead. Question number 27. Question number 27. So if the number of turns per unit length of a coil of solenoid is doubled, the initially number of turns were n, and now it is 2n. Cell inductance of the solenoid would be how much? So basically, I need to know how L is dependent upon number of turns. Okay. So I initially also told you that for any geometry, L is directly proportional to n square, which we did in this question, I guess. Here, L is directly proportional to n square, which we told you. L is n phi by I, phi is replaced with BA, and then put any formula for magnetic field, you will get two n's, one here and one here. So L is directly proportional to n square. So this formula also works for solenoid. Okay. So we will use this thing only. So see here, the resistance of solenoid is given by this formula. So using this formula, we can see that it is dependent upon n square. Why so? Because phi is Li, and for solenoid, phi is given by B into A, and in case of solenoid, B is given by mu naught N into A. Okay, so mu naught Ni into A is equal to Li. So L would be mu naught N I will cancel it, give you A. Okay, and then it is number replace N with number of turns per unit length. So it would become N by L. Okay, so it would be mu naught N by L, and let's say this is for one turn. For total number of turns, it would be N. So multiplied with n, and you will get mu naught n square A by L. I hope you got it. Uh, B equals mu naught n I. There n is nothing but number of turns per unit length. So total number of turns is n. Per unit length it will be L. So this is for 1 turn. For n turns, it would be n into mu naught n by L multiplied by I. Equate this to Li. I and I will get cancelled, and you will get L equals mu naught n square A by L. Of course, this A will also come for BA. So here A will also come. So this thing is my L, and from here also I can see that L is directly proportional to n squared. So they are saying that n is double. So initially L1 by L2 is nothing but n1 square by n2 square. Okay. So L2 by L1 would be n2 squared by n1 squared. L2 by L1 would be n2 is 2 times n1, 2 n1 squared by n1 squared, which would be 4 times L1. So my L2 is 4 times L1, which means it would become 4 times option number D. Cool. So I hope you got it. It was again a simple question, nothing tough here. Just use the simple logic that self-inductance is directly proportional to the square of number of turns. You will easily get option number D as your correct answer, which is correct answer D. Cool. So moving ahead, question number 28. An inductor must store energy in its electric field, coils, magnetic field, both electric and magnetic field. So basically, we are being asked the inductor stores energy. How inductor stores energy? So we know that capacitor stores energy in form of electric field. Please remember these things. These are small things, but this will give you +4 marks in JEE Mains if you know these things. Similarly, an inductor stores energy in form of magnetic field. So I will write it here again. Capacitor stores energy in form of electric field. Similar way, inductor stores energy in form of magnetic field. Cool. So I hope you get that. It is again a simple one, direct question. +4 -1. If you know this, you will get +4, otherwise -1. So these things are very small things. So please get a hold on all these type of concepts. So moving ahead, number 29. The total charge induced in the conducting loop when it's moved in the magnetic field depends upon how upon. Same question we did earlier. Q is equal to V. Sorry. Q equals integration of I dt, and I is given by EMF induced divided by R. So it would be integration E dt by R. E can be replaced with d phi by dt into dt by R. So dt and dt will cancel, and I'll get integration d phi by R. Q would be integration d phi divided by R. So it is dependent upon total change in magnetic flux. Total change in magnetic flux upon resistance of the loop. Okay. So this is dependent upon total change in magnetic flux. It's option number C. In case of EMF induced, it is d phi by dt, which is rate of change of magnetic flux. Okay. And this is for charge for EMF. Cool. Option number C is our right answer to this question. It is again a repeated question, so no worries for that. Question number 30. You can write it like this: integration d5 by r can be written as phi 2 minus phi 1 by r. Final flux minus initial flux divided by r. Let me write it clearly: phi 2 minus phi 1 divided by r. Okay. Okay. So moving on to question number 30. Current in self-inductance L equals 40 millihenry, which is 40 into 10 power minus 3 henries. Is increased uniformly from 1 ampere to 11 ampere. So delta is 11 minus 1, which is 10 amperes. Okay, in 4 milliseconds. So delta t is 4 milliseconds, which is 4 into 10 power minus 3 seconds. So delta I by delta t I can calculate. It would be 10 divided by 4 into 10 power minus 3. It would be 10,000 divided by 4. It would be 42500. So it would be 2500 ampere per second. Cool. So EMF into Z enough. So EMF is given by minus d phi by dt. Phi equals Li. So d phi by dt equals minus L di by dt. Sorry, minus. And from here you can write EMF equals L into di by dt is 2500. L is given to us as 40 henries. 40 10 power minus 3 henry into 2.5 into 10 power 3. I can write it like this. So this and this will cancel, and you would be left with 40 into 2.5, which is 100 volts. Cool. So option number A is our right answer. I can check that. Yes, option number A is our right answer. Similar way, E is L di by dt. L is this much. Di is 10 amperes. Dt is 4 milliseconds. And E is just do L di by dt. L is this much. 40 millihenries. This is my di by dt. Solving this, multiply this, you will get 100 volt as the final answer. Please don't confuse the negative sign since we are talking only about magnitude. So we are neglecting negative sign. Okay, so don't confuse with this negative sign, negative terminology, and all this kind of stuff. So this was my question number 30. So now moving on to question number 31. 31. So a thin semicircular conducting ring PQR like this. Of radius R is falling with a spin vertical in a horizontal magnetic field B as shown. So see, ring is like this and magnetic field is going inside. Okay, so we know that since ring is like this, so when you will use your right hand thumb rule, you will get the area vector of this thing also inside only. So basically area vector is perpendicular to the magnetic field. So when we will calculate flux, cos theta would be cos 0 again, that would be 1. Okay, so I hope you got it, that area vector is again parallel to this magnetic field. In a horizontal magnetic field B as shown in the figure, the potential difference developed across the ends of the coil when speed is V. So basically it is traveling with the speed V. So I need to again tell what is the EMF induced. Okay. So please first understand this thing why theta is 0, because the area vector would be again in parallel direction to this magnetic field. Inside or outside doesn't matter because we are not considering with the sign here. So same thing, rate of what would be A? A would be pi r square by 2. Why pi r square by 2? Because it is semicircle. So dA by dt would be pi by 2 common, 2r dr by dt. So 2 and 2 will cancel and we would be left with pi r dr by dt. Okay. And EMF is given to us. Well, EMF is nothing but d phi by dt, which is minus b dA by dt. So it would be equal to minus b pi r dr by dt. Cool. So anything is given to us. So they are saying minus b dr by dt. Okay. Speed is given to us as v. So speed is given to us as v. So we can use that. So dr by dt is nothing but the change of the rate of change of radius, which is given to us as b. So let's use that. It should become minus b pi r into v. Okay. So let's see, minus b pi r into v. So EMF would be b pi r v, which is my option number. Hmm. So I think C would be correct option here, not D. Let me check once. So we get this thing. We get dA by dt to be equal to pi r dr by dt. Okay. And they're saying that the potential difference developed across this ring, if it is across the ring when its speed is v. So the speed of the ring is v. Oh, okay. So basically, this is v. If I will replace this semicircular wire with a straight wire, then basically it would be 2r instead of r. So this v is not dr by dt. Please, please see this. I think we get wrong here. So this is not, basically v is d by dt of 2r. So this 2 will come outside and we will be left with 2 times dr by dt. So dr by dt is given by v by 2 instead of v. Okay. So please put v by 2 here instead of v. Okay. So here I can put v by 2. Cool. So I hope you got it. So this was my question number 31. Please remember this thing, that here I am replacing this semicircular wire with a straight wire. In case of the straight wire, this dr by dt, v which is given to me, which is speed of the straight wire. So instead of this r, because in a semicircular cycle, this thing is given by 2r. So instead of dr by dt, it would be d of 2r by dt. So you can take 2 outside. It would be 2 dr by dt equals to v. So dr by dt is nothing but v by 2. Okay. I hope you got this one. So it was a good question, nice question. Again, asked in JEE Mains only, but a nice question to be asked. So instead of this, it would be D part is our right answer because of the factor of 2. So moving on to question number 32 now. A wire loop is rotated in a magnetic field. Okay, so here omega will come into picture. A wire loop like this is rotated with a speed omega. The frequency of change of direction of induced EMF is basically how direction will change. I have to see to that. I have to see that. Okay. So let's see. It is basically rotating like this with let's say omega. Okay. So I know that when it is rotating, flux will keep on first will change direction because EMF is given by minus d phi by dt. It is basically from here I can see it opposes the change in magnetic flux. Okay. So it is something like this. It will first be positive and then it would become negative. Okay. So from graph it is clear that direction is changing once in a half cycle. So basically it is going like this in first half and this in second half. So frequency is nothing but number of cycles per unit time. So basically in half cycle, that is for this much distance, pi, it is changing like this and then again this. Cool. So this is a case of periodic EMI that's shown here. So since it is changing twice in one cycle, like this, first and second, so it would be twice per revolution, which is option number A. Okay. So I hope you got it, because since we are rotating it with speed omega, so I can say that using this graph, it is changing twice. First, it is positive in this much, positive, and then negative. Of course, this graph is between E and time. Okay, so it is changing twice in one loop. So frequency of change of direction is twice per revolution. It is changing twice per revolution. Once it is positive and then it is negative in half cycle. Again, a simple one. Just if you know this graph, then you can easily do this question also. So moving on to next question. Question number 33. Current of 2.5 ampere flows through a coil of inductance 5 Henry. So I is given to me as 2.5 ampere. Inductance L is given to me as 5 Henries. Magnetic flux linked with the coil is asked. So what is B? They are asking me. Okay. Not B, sorry, magnetic flux. So it would be phi. Okay. So what is phi? They're asking me. So again, a very simple question actually. Phi equals L into I. Inductance into current flowing through the wire. So inductance is given to me as 5 Henries. Current is 2.5 amperes. So you will get 12.5 Weber. Unit of flux is Weber and unit of magnetic flux is Weber per meter square, which is given by Tesla. And why so? Because flux is nothing but B into A. So if it is Weber, B into A unit of area is meter square. So from here, I get the unit for B vector to be Weber per meter square. Okay, so just a random thought. So I told it. So basically, this is again a simple question. Just use this formula phi equals Li, and you will get your final answer, which is option number C. So now moving on to question number 34. Okay, so I think this is a nice question. A coil of resistance 400 ohms placed in a magnetic field. If the magnetic flux linked with the coil varies like this, 50 t square plus 4, then what would the current at t equal to 2 seconds? So for this, I need to use this formula that Q is given by integration of d phi by r. So how I got this formula, I guess you know, and then I will use I equals Q by T. Okay, or you can use Q equals integral I dt. I you can write as EMF induced divided by R. So it would be EMF induced divided by R into dt, which would be given by d phi by dt into dt divided by R. Dt will cancel. It would be integration of d phi by R. That's what I wrote here directly. Cool. So let's see. Same thing is done here. So EMF induced given by E by R, and we know that EMF is d phi by dt. Phi is given to me as 50 t square plus 4. So it would be minus d by dt of 50 t square plus 4. That would be 100 t. Okay. So this is my EMF. So I would be E by R. That would be 100 t divided by R. So I need to calculate what? I need to calculate current at t equal to 2 second instant, which is I at t equal to 2 seconds. That is 100 t by R. How much was our resistance? It was 400 ohms. So just put 400 here. You will get 2 by 4, which is 0.5 amperes as your final answer. Okay. So option number A is our final answer. Again, a simple one. Just use EMF equals d phi by dt. Differentiating it, you will get voltage, and current is given by voltage by R. R is given to you. Voltage you calculate from here, and you will get the value of I, which is the current required in this coil. Cool. So I think it was a tough question, but it was not. So it is again an easy question. You have to just use simple formulas, do simple mathematics, and you will get your final answer. So moving on to the last question for today, question number 35. The current I in a coil varies with time as shown in the figure. So the variation of induced EMF is how much? They are asking. Okay, so it is a nice question. So let's see. So first, let me draw out the diagram here only. It is like this. Okay, it's going like this, then this, and then like this. Cool. So this point is t by 4. This point is t by 2. This point is 3t by 4. Okay, and this point is t. Okay, and this is between current and time. Okay, so now I need to calculate EMF induced current. So I know that EMF induced is given by minus L di by dt. Again, from the same equation, phi equals Li and EMF equals minus d phi by dt. Then I will get this thing. Okay. So in first t by 4 seconds, my current is increasing with time. So this thing would be positive. So my EMF would be negative. Why? Because we can see that current is increasing with time in the first t by 4 seconds. Okay. So EMF would be negative as shown here in first t by 4 seconds. Okay. Then in next t by 4 seconds, it is constant as I can see here. So di by dt would be 0 in this case. Why so? Because current is becoming constant in this case. So this is for t by 4 to t by 2. So in this case, E would be minus L di by dt. That would be minus L into 0. That is 0. So 0 EMF would be induced when the current is in this phase from t by 4 to t by 2 seconds. Okay. And then going on to the last section, not last, second last. In here, I can see that current is decreasing with time. That is, as current is increasing, as time is increasing, current is decreasing like this. So in this case, my di by dt is negative. So EMF is given by minus L di by dt. So negative into di by dt is also negative. So negative into negative will become positive. So it is positive from t by 2 to 3t by 4 seconds. Okay. And the last option again, my current is constant. It is equal to 0, doesn't matter, but it is constant. So since it is constant, so di by dt is 0. And if di by dt is 0, then EMF given by L di by dt will also become 0. Okay. So it would be something like this. Firstly it would be negative, then 0, then positive, then again 0. So it is negative 0, positive 0, something like this. So let's see which graph is like this. So here it is negative, then 0, then positive, then again 0. So ignore these lines, these are just for transitions. So these lines are just for transitions, so neglect these lines. So here it is negative, 0, positive, 0. Satisfying this case. So let's see others. So here it is, no, here it is also positive. Here it is again positive, and here also positive. So this is wrong. Then here both are negative. So this is also wrong because both are negative. And in this case, it is starting from positive and becoming negative. Instead, we need initial negative, then 0, then positive, and then 0. So this is wrong. So only one option is correct, which is option number A. So only option number A is correct. This one, because this suits us. This suits our methodology. Okay, so let me erase all this. So option number A is only correct option. This one, initially negative, then 0, then positive, and then 0. So option number A is our correct answer to this question. Okay. So this was the last question for today. I hope you got this chapter EMI electromagnetic induction. When we scroll through each and every question, we can easily see that only these two formulas. First, EMF equals minus d phi by dt, and phi equals B into A. For self-inductance case, it can be written as Li, and for mutual inductance case, it can be written as Mi. So if you know these things, then you can easily solve each and every question from this chapter. But just remember one thing, that certain things, like I told you in the lecture also, like inductor stores energy in form of magnetic field, capacitor stores energy in form of electrical field. These type of questions you should remember, because these save your time. If they come in JMNs, you just mark these things and move ahead to other sections like mathematics. So again, it was an easy one. After magnetism, if you do this chapter, you will easily get its concepts, and it will you will easily go through it. Again, for J advanced, you might need to learn certain advanced things like solving inductor equations during charging and discharging. So those things are important from JEE advanced perspective. So look through them also. But for mains, it's enough. And I hope you also learned in these two lectures which we had taken on electromagnetic induction. Okay, so this is it for EMI. Rest we will meet in our next sessions. Okay, so it's all for today. Thank you.